All right, I think we're gonna get started. So, hey everyone, I'm Chris. I'm part of the West Lab. I'm going to talk to you today about RMG for catalysis. There's kind of some nice little dovetails with the settings that how I just talked about that we're going to be talking about a little bit today in here. So it's fortunate that I'm coming after her. Just some acknowledgements at the beginning and kind of who to look for if you have questions about this. I think, in addition to, all the support we have with the hackathons and developer hours and like talking with, all y'all at MIT. This is also developed with Franklin Goldsmith's group at Brown University. So Katrin and Bjarne have in particular done a lot of contributions to the database. And then Katrin is kind of working on it a little bit less now that she's graduated, but Bjarne is a postdoc in Franklin's group and he's been actively working on it quite a bit. And then over in our group, Sevi at this point, I think, me, and then Emily is recently graduated and has done all the work. So heterogeneous catalysis in RMG, we're able to model gas phase chemistry with a solid metal transition metal catalyst. We haven't quite incorporated liquids into our modeling yet. We also haven't incorporated things like alloys or kind of different surface like geometry. But it's still pretty powerful for just the gas surface single crystal facet case. So I've sent out an email that all of you should have gotten that has, it's one of our examples, actually. It's an input file for the CPOX mechanism, or the catalytic partial oxidation of methane. I'm going to be walking through it, but if you can't quite keep up, we can still talk about it afterwards. And, we can maybe, if we have a break, we can go over any difficulties you're encountering. So like, don't get too hung up on trying to keep up with what we're doing, but it's kind of there so that you can add things and do things as I'm talking about this. Good place to start is with species in RMG. We have, the adjacency lists, which is how we represent things. For surface species, there's the added layer of having a surface metal. For that in RMG, we just have this made up atom X, which is, not on the periodic table. It's just our surface site. So for, adsorbed CH3 or OCH3, you'd have this sort of adjacency list and specify it the same way. You'd say how many bonds you have to each atom, et cetera, et cetera. So for this X atom type, I think we've actually changed this a little bit. So now at this point, you can actually specify X for any sort of surface site, whether it's a vacant surface site or an occupied surface site. But it's meant to represent the metal that you're using within your mechanism. So we have platinum or nickel, but also we've added a whole slew of other metal atoms to the database, including rhodium, iridium, etc. But you basically just use this X atom as your single surface site. There's a number of species and catalytic mechanisms that have, they're weakly adsorbed. I think it's usually like under like 100 kilojoules per mole for the binding energy or something like that. But they're kind of like a two-dimensional gas on the surface. So the way that we represent these, where there's not a specific like, single, double, etc. bond from your add atom to the surface, is as a van der Waals species. So for these, it's pretty straightforward to represent them. You just don't make a bond to the surface atom. You just have the X atom by itself and draw your species as you would for CO2, H2O, etc. So for thermochemistry with these species, we have another, I guess, added layer to our typical like thermochemistry estimation using group additivity. So for group additivity, you take the gas phase molecule and you break it up into groups and you attribute certain contributions to the entropy, Gibbs free energy, etc. For linear scaling with surface species, we have the initial gas phase species, which is from group additivity. Then we have the adsorption correction, which comes from linear scaling, which I'll explain in a couple of slides. And then we have the so we have the adsorption correction, which actually that's not from linear scaling, that's from an adsorption correction database that we have. The adsorption correction is basically similar to group additivity. You take a molecule and you try to group it with similar molecules in an adsorption correction database, and you apply the thermodynamics from the similar group to your estimated model in order to determine how the enthalpy changes when it adsorbs to the surface. This delta binding energy is from linear scaling. So that delta binding energy is going to change your metal that you're adsorbing to. So if you have an initial value for, say, CH3 on copper or platinum, and you want to get it on iridium, the delta binding energy will be applied to that metal as you're going from platinum to iridium. So just a couple tips in terms of species when you're constructing surface input files. Howie was talking about the maximum carbon, oxygen, etc. atoms that you can have. There's also maximum surface sites that you can specify for your generated species. So just kind of the current state of RMG cat is that we're better at monodentate and bidentate species. Tridentate, things beyond that, like if you have like a ring structure adsorbed on the surface, like it gets very complicated. We haven't quite, gotten things figured out for that. So I think just from kind of our own little group knowledge is if you specify 2 surface sites, that'll keep your problem tractable, and also specify less than 3 carbon atoms, because just given what we've calculated in our thermodynamics database, we don't have great estimation for larger molecules.
Obviously, synthesis of larger fuel molecules is the goal, but it's just the data's not there yet. It's just the database.
It's a big problem, and if you look at a paper for like propane, etc., on a catalyst surface, it's very complicated. So it's keeping your problem tractable. It's best to specify these 2. So I guess just in the interest of time, I'm not going to dwell on like our example steps too much, but I think we have an input file that I've sent to all of you. What I would suggest is trying to add, in addition to the species that we've specified as the methane, oxygen that we're reacting, you can specify intermediates in your input file, and this will often help your mechanism if you specify known or identified surface intermediates. So I put adsorbed oxygen, physisorbed CO2, and then adsorbed carbon monoxide. And then in addition to that, when you're putting together this input file. As I've shown on the last one, if you constrain your mechanisms on generated species constraint input block, you constrain it to 2 carbon atoms and 2 oxygen atoms and 2 surface sites. That should keep your problem fairly tractable for the CFOX example. So kind of delving into thermo a little bit more, similar to the group additivity trees that we have for the gas-based species. We have hierarchical adsorption correction trees that we put together. This comes from a lot of data that was generated by Katrin and also Garnet at Brown. So this helps you determine when you have a gas phase molecule that you've already estimated thermochemistry for. It'll help you determine how your enthalpy changes when you adsorb that molecule on the surface. So for changing your thermochemistry based on what metal you're on, we use, which I alluded to earlier, what's called linear scaling relations. So these are kind of posited a while back, but by Abel Peterson in a paper that I think I've cited like probably over 100 times at this point. But they're basically a linear correlation between binding energy and what's called bond orders. So, if you have a C atom or carbon atom, your bond order is just how many bonds you have to the surface metal atom. So you can construct these linear scaling relations for carbon, nitrogen, oxygen, sulfur, like a whole slew of heteroatoms that are interesting. And they allow you to basically change your enthalpy via your binding energy for different species that you have absorbed on the surface. So for this top one, we have carbon, which is quadruple bonded, so it's got a bond order of 4. And we're going to change it by 0.32 electron volts to get it to nickel. So basically from these the plots that I had earlier, that's like the slope of the line basically. For this I guess CH2OH, it's kind of like methanol. We have a bond order of 1. So in order to scale it from platinum to nickel, we take the 0.32 electron volts that we have in the initial one for the carbon atomic binding energy, and we multiply it by that 0.32 electron volts. For something like oxygen, it's similar, but since we can only have 2 bonds to the surface, for the single oxygen atom, we scale it by, this change in the binding energy. And when we have only 1 single bond to the surface, we'll scale it by 1/2. So it's 1 over the maximum number of bonds. So this is pretty powerful because it allows us to estimate thermochemistry for essentially any adsorbate that we have. Some of the assumptions of it are, you're looking at for these scaling relationships, the data that they have is for a single metal facet. So it's for the 1-on-1 facet on, platinum, nickel, etc. It's assuming that you're taking the molecule and putting it at its like lowest energy configuration on that surface. If you use a different facet, then there can be a different configuration for that atom, and it kind of throws that assumption out the window. So it's better to use these with just a single metal facet and use them, don't mix and match like the 2-on-1 and the 1-on-1 facet. But it allows us to take, if we have an unknown molecule, we can take gas phase estimation using group additivity, estimate the thermo for that species, And then we apply our absorption corrections and absorb the gas phase molecule to the surface. And then if we're doing it on a metal other than platinum, we can change it using the linear scaling relationships. Just because I've been saying platinum a lot, what is special about platinum is that it's not exactly special, it's just kind of convenient. We've done a lot of calculations for platinum. So most of the information in RMG database is for the platinum surface. This is changing. We're doing more thermochemistry calculations for other surfaces and also for other metal facets. Additionally, I think since the last time we presented this, we've added in a metal library that has binding energies for a whole number like of common metals, copper, nickel, rhodium, palladium, etc. That come up in surface chemistry mechanisms. And we also have them for several different facets. I guess just to clarify though, like this isn't combinatorial. Like we have all these metals. I think for copper, we have like Cu 111, 100, and 211. I don't know if there's a copper 0001 surface so you can generate, but like we have kind of a smattering of these. We have all of these metals, but we might not have nickel 211, for example. But essentially, like we're kind of beefing up this database so that we can do linear scaling for different metal surfaces and different metal facets. So when you're putting together an input file, when you're specifying a catalyst, you can either, and it's within this catalyst properties block that we made for RMG Cat. You can specify the name and the facet. So for platinum 111, you could put PT 111, or you can be as specific as you want and kind of customize it with your own binding energies you specify. And this is useful if you're kind of doing like a screening study. You can just kind of change carbon binding energy by itself or oxygen binding energy by itself, etc. And you also can specify a surface site density for it. If you kind of want to go and test your own type of catalyst surface. So for the example, you can put in, these are the values for platinum. So it's kind of 6 of one, half dozen of another, because the input file specifies platinum 101, but more or less just to have you put them in yourself. You can put in these binding energies and then also surface site density of 2.5 times 10 to the 9. And I'll be sending out an answer input file that you can check your answers against. So again, don't worry if you're having trouble keeping up. So we've gone over species, thermo, and then I'm going to touch on just the kinetics that we have that's unique for surface reactions. So I think initially, like since, when we first put together RMG Cat, I say I wasn't even around for it. I think it was Richard and Franklin that put it together. There were a limited number of reaction families. This has changed. We've added in quite a few new reaction families. In particular, Emily added in a lot of van der Waals reaction families, and Bjarne from Brown has added in a lot of these abstraction beta double BBW. It's basically similar to like the families we already have in there, but it's at like the beta position, so it's like one carbon over. So we've added in a lot of reaction families. I think I was having a discussion during office hours this morning with someone who's using RMG Cat, and I think kind of the downside of having all these new reaction families, like we can guess at a lot of different chemistry. But we're in the process of like filling in rate rules for those new families. Like we have that the chemistry is possible, but we don't necessarily have the best estimate for that chemistry. So, you know, constructing rules for those is kind of time consuming, but like it's in the process of getting updated, but it's better to kind of be restrictive when you're constructing your RMG cat input files, just because, you know, if you have too much chemistry, it can kind of like obscure like your mainline pathway. So restricting again your number of carbons, your number of surface sites, that'll help you kind of keep your problem tractable. Because we, you know, have added a lot of new possibilities to what the molecules can do with each other. One little thing is when you're putting together an input file and you're specifying where you're getting your thermo and reactant stuff. So within the database block, like with the default families, we've also specified recommended surface families. They're essentially surface families that we have used in our mechanisms and found that the rules are stable and, you know, give you likely chemistry. Because for some of these, like for some of the, we've added in a number of bidentate families. We're still kind of working on getting them to play nice with RMG. So it's the ones that work well, basically, well enough for us to be confident in the mechanism we get with them. So an RMG is estimating reactions. It does it similarly to how it does it with, you know, the rate rules for the gas phase families. I think what we call our, instead of Evans-Polanyi relationships, we call ours BEP, which is Bronsted, Bells, Evans, Polanyi. I think it's Bells, Evans, Polanyi. Just because it pertains to the surface. The difference, I guess, when you're creating these rules or updating these rules is the units for surface reactions are obviously going to be a little bit different. So for gas phase reactions, it's in moles per meter cubed. For surface reaction rates, it's going to be some combination of moles meters squared second. It's important to kind of make sure that you have the correct units, because it does, like, it's not as close to your intuition as like the moles per meter squared reaction rates might be, just because of, like, you know, undergrad kinetics and stuff. We don't really use surface reaction rates as much. But just be aware if you're specifying rate rules or adding reactions to a library in RMG that your units are consistent, because we do check them in RMG, but, like, you know, it'll keep you from going nuts trying to troubleshoot errors, I guess, when you're adding stuff in. There are, I guess, 4 types of reactions, but like 2 main ones. So there's like the surface Arrhenius reactions, and there's a sticking coefficient. Within RMG, I guess maybe this is a little too under the hood, but we have the surface Arrhenius BEP and sticking coefficient BEP as well. But like for the intents and purposes of this explanation, surface Arrhenius and sticking coefficient are the actual, like, kinetics that are happening. So for surface Arrhenius, it's similar to your Arrhenius expression, except the units are a little bit different. For sticking coefficient, the difference with these reactions is you're looking at, for the K, you're looking at a probability instead of like, I guess with your A factor, like you could look at all of these, like, I guess is a probability. But your sticking coefficient equation is you have, this. I guess S, which is your sticking probability. And then you have your, KBT over 2 pi m. This is, I guess, like kind of standardized, so like if you're looking at like a Chemkin file or if you use Cantera or something like that, they'll have a format for implementing sticking coefficient type reactions. We've also, for both the surface Arrhenius and for the sticking coefficient, we've added in the ability to specify coverage dependent kinetics. So for coverage dependent kinetics, it's kind of just an add-on to your normal rate expression or rate constant expression, where you have past this pi for each coverage dependent species, which is a K. You'll have modifiers for the A factor, the temperature exponent, the activation energy. So the way that those are specified is using this coverage dependence expression here. So you can specify it for NX, HX, if you have within your mechanism, and you can specify in a dictionary what you want for your A factor modifier, temperature exponent modifier, and activation energy modifier. One thing I will say about this is, so you can specify them, and we have a number of libraries that have coverage dependent kinetics. We don't currently have a way for RMG to estimate coverage dependent kinetics, so it's not going to propose a new rule that has coverage dependence. So
Can you spell thermo? So if I put it coverage dependent in the rate.
Yep.
I put it just in the forward rate and then the thermos computed. Just right, if you get equal.
Coverage dependent thermo is not in Chemkin. We recently added it to Cantera, but not yet added it to RMG.
but I think
So you're right, the first thing to change when you have coverage is the thermo. And that's why it's noticing, but that's not implemented in most simulation software. So we don't do that yet. So yes, the reverse would be from the thermo, which hasn't changed.
So the reverse would not be coverage dependent.
The reverse would be coverage dependent to the same amount.
Exactly. the same
Yeah,
way.
yeah.
So
So if you
Yeah.
speed up the forward, you speed up the reverse. At the
Yeah.
moment.
I guess you get the KF with the coverage dependency, and you get the KR.
But coverage dependent thermo is something we should look.
Yeah,
We just added it to Cantera. So it's possible today.
it's possible. So it has a lot of complexity. But
Yeah.
Yes. And maybe just a comment about this is that.
Yeah.
For the thermo. The insistency of oxygen. Maybe CO also. Oxygen and CO have very strong effects on the
Yeah.
dome. And so. Then people think you need coverage dependent. For the thermal and possibly also for the kinetics. For the other ones, I think it's not, since you can. Might understand.
Yeah, I think like what would probably be good, and like there's a lot of things that would be better than nothing, you know, like having some sort of, but for kinetics estimation, having some sort of simple, like, you know, coverage dependence expression for every other species. For thermo, I feel like we could find something that's maybe also similarly straightforward, like where we, you know, just base it off of the coverage of everything else, and we don't take into account, like, you know, steric effects or anything like that. We just treat everything as the same. So that's something to consider, and maybe we should try to implement something like that before we put in our, you know, very complicated coverage dependent thermodynamics expressions. It is very important for a lot of surface mechanisms. If you're including a library that has coverage dependence, or you've created a library that has coverage dependent kinetics, you can specify that you want your mechanism to use the coverage dependent expressions, by setting coverage dependence equals true within your input file. I guess, as I said earlier, RMG cannot estimate coverage dependent kinetics. It can only use the ones that you put in. And also it can't estimate coverage dependent thermodynamics currently. So that's covering kinetics, thermodynamics, species, and now just real quick, talk about the reactor. This is something I'm currently working on, but we don't use an RMS reactor for the gas surface mechanisms, which it's actually pretty straightforward to implement, so it's a little silly that we're not. So hopefully coming soon, we'll have a RMS reactor for heterogeneous catalysis. But for the surface reactor, we use constant volume isothermal batch reactor. It has, a gas species or gas reactants and a surface associated with it. And then we initialize it with gas mole fractions and also surface coverages, so you can specify what's already on the surface within your batch reactor. If you specify something other than just an empty surface, that can help, in terms of adsorption is a very quick reaction. So if you start out with just a bunch of gas phase species and nothing on the surface, your flux criteria is going to be a little bit biased because it's looking at, all of your absorption reactions. And everything from then on might be a little less significant when you have H abstractions on the surface and stuff like that. So it's important to keep in mind. And then it solves it in terms of the number of moles. And then rates are all converted into per volume basis. So when you're setting up a surface reactor, I've just kind of gone through what I think is everything that might be important. Some of these are probably a little familiar from the minimal example. You can specify a range of temperatures for surface reactors, but you cannot specify a range of pressures. This is something that should, I think, be implemented in the future, but it's kind of non-trivial. I've made some attempts at it. You can specify if you're doing sampling like this with a range of temperatures, you can specify the number of simulations. Similar to the gas phase reactors, you say what you're actually feeding into it. Additionally, you can specify your surface coverages. So over here we have an empty surface, so x equals to 1. Another added thing for surface mechanisms is you have to specify the surface area to volume ratio. And then for your conversion criteria, I think one thing I would like to say about this is kind of similar to the comment I made about the adsorption reactions. It's a little better to focus on your termination conversion and your termination time for the specific reaction system that you're looking at. Termination rate ratio is useful, but I think you want to be a little careful with it, or a little more careful with it with surface systems, just because it's, again, looking at all the reactions happening, and your adsorption and desorption reactions might dominate that a little bit. So it might not catch things that are important, but they're not quite as dominant as adsorption, desorption stuff on the surface. For this example, specifying it allows us to run it through pretty quickly. So this is the last piece of additions to make to the input file that I've given all of you. So you're going to want to set your temperature sampling to 600K to 2000K with 4 simulations, which is similar to what I have on this page. Set your initial mole fractions to 0.15 for CH4, 0.15 for O2, 0.6 for N2. Stop the model generation at a rate ratio of 0.01 or after 10 seconds, or after 95% methane conversion. What that looks like is like what I have here, so 10 seconds, termination rate ratio, you can set it to 0.01. And then for termination conversion for instead of CO2 0.15, we'll do CH4 0.95. And then this last piece, you don't have to do this, I think in the example, it's set to what our default value is, I think, which is 10 to the -5. But it finishes a lot quicker if, for the tolerance move to core, if you set it to 0.1. I think it finishes for me in about 2 minutes. And then to run the example, you do what I presume you've already done within this training. For other input files, you'll do Python JL, the path to your RMG.py executable, or your RMG.py program, and then the path to your input file. So any questions about this, I can field, I guess, after. I'm not quite sure how we're doing on time. Okay. But just to kind of show, these are a number of publications and presentations we've had about RMGCat. We've had successes, especially with, carbon chemistry. I think we haven't quite delved into the ammonia, nitrogen chemistry, in terms of stuff that we've actually published. But we have incorporated a lot of ammonia kinetics, and I think some thermo, so maybe that will be coming. Some of the challenges upcoming for RMGCat are, we don't have a ton of data still. We're kind of generating more data as we go for both thermodynamics and for kinetics. It's a little bit more complicated, I guess, because with surface chemistry, in addition to your molecule that you're doing a EFT calculation for, you're also doing your molecule in relation to this giant metal slab that I have shown here. LSRs, so the linear scaling relationships, are great for screening, but they don't work for everything, and they can break if you have things like an alloy system, or like single atom alloys, especially, I think, are known to break linear scaling. We don't have site specificity. We don't have too many kind of more complex or interesting surfaces, like bimetallics, scaffold, zeolites. No coverage dependent thermo. And then also I have here just some of our species representations aren't quite exactly what's going on the surface. So this is formate, which is an important molecule in a number of mechanisms, but methanol synthesis. It forms this kind of bidentate structure, but with our, our kind of bond order preservation when we're constructing these species. We can't have 2 oxygen atoms bound to the surface and also bound to that central carbon, I guess, in a bidentate formation. So we have it represented as we have here. So having some sort of way to represent like half bonds and stuff like that with surface species or kind of resonance structures is something that I think Bjarne from Brown is working on. In the future, we'd like to have coverage dependent thermo, site specificity, linear scaling, or some sort of thermo estimation, possibly machine learning for facets beyond the one-on-one surface. Stuff that allows us to do alloys and zeolites, which is kind of what I'm working on for my final project. And then I guess, yeah, just a lot of this stuff has been funded by a grant from the Department of Energy, so just kind of acknowledging that. So yeah. Anybody have questions or comments? Zoom or in here?
You had X representatives of the sites. Were there any catalysts that have two different kinds of surface sites?
Yeah, so
And how would you represent that?
in terms of like, I guess. Do you mean like if you're bound to?
Like in a pocket or some top of the.
I see, so like, I guess that would be like the active site, or like where we think chemistry happens, or what, like an important site on the surface. Yeah, there are like, especially like stepped surfaces, I think like there's like a number of different configurations. I think for currently what's in RMG, for the one-on-one surface, the amount of other configurations that you could have for something, just looking at like the probabilities of them like absorbing in those different spots, it's so low that it's like not really worth taking into account. But for things beyond the one-on-one surface, it is important. So you know, moving on, it's something we'll have to figure out, but for the current facet in RMG, or the current system we have in RMG, it's not really super important.
So for now, everything's assumed to be in its favorite site. So if you're doing the DFT, you consider, I put it in the top, or I put it in a hollow, I put it next to three things, and then I pick the favorite, use the thermo for that, and then the mix. So everything's assumed to be in its favorite site. Bullet point number 2 on future features, site specific. So if you're trying to track, well, actually, we've got some edge sites and some top sites, and a different number of each. These ones get occupied, those don't. You then got to track 2 different, like, species concentrations of different sites. And that we don't get. We just have one. Okay.
So it's shared for all the different reactions.
That would be
favorite.
Yeah, so the follow-up question, that means, like, if they both have to absorb onto the surface with what we act, are they all within a tight heating or the same size, the longest, almost the same?
Yeah.
It's mean field, so it's just kind of per surface area. SEMI's working, we've got a DOE project is moving towards kinetic Monte Carlo, where you then actually have specific sites, you know where things are. And so SEMI's working on getting RMG coupled to that, basically, I think. Yeah, I think that our biggest challenge is just lack of data, and therefore the estimates are really bad, and therefore, as we were hearing this morning, if your estimates are bad, your model goes haywire.
I think also it's like, not even like, cause there are things like the Open Catalyst project where there's a large amount of data, but it's a consistency thing. Like for gas phase stuff, you have like the ATCT for like making sure that everything's kind of on a consistent basis with each other. And I think somebody's actually working on that for like surface chemistry, but like, you know, if you use a different DFT functional for something, or if you use a different work function, which is like how you calculate what your absorption entities or like your surface thermodynamics, your answer will be like, if you're consistent with itself, you'll still get the same answer. But if you have heterogeneous data from different DFT sources, then you can kind of like make a mess of it and have like different answers that you get. So it's like we're trying to generate stuff that in particular uses functional called beef VDW, which allows us to do like kind of uncertainty for our surface species. But if we draw it from different sources, it's like we have to take into account like what their reference state was and stuff like that. And it can kind of get a little tangled. So it's easier to kind of do your own calculations. Well, I guess, I don't know if. Is there like, I could put my email on something or send it out, I guess people probably already have it from that email, but you know. Feel free to reach out, you know. Like, make a message or send me a message or something like that, if you have questions about constructing input files or anything like that. I'm happy to try to help.
Thank you, Chris.